Hi, let us see EMI part 2 motional EMF. Let us consider a rod of length L which is in a perpendicular magnetic field B of length L, which is moving with a uniform velocity V. In this case, if you consider metallic rod, the E electron will experience a force from Fleming's left hand rule BeV downward. After some very small interval of time, the electrons will accumulate at this end. So there is a loss of electrons here. So this end will acquire a positive charge and this end acquire a negative charge. So there will be electric field created from positive end to negative end. So because of this electric field, the force on electric field will be E. There will be some instant at which the force due to electric field and force due to magnetic field will be equal. So E is equal to BeV, E is equal to BV. So that is the electric field. But from electrostatics, you know, the potential difference is equal to E into L, and that is equal to BLV. So this is the induced electric field and this induced potential difference. And this electric field which is induced in this rod is called a non-conservative electric field. It is not like a electrostatic field. So it is a non-conservative electric field. Now if you see here, again consider the same rod of length L moving with the velocity V in a perpendicular magnetic field B. So let us suppose if we connect a external resistance R which is not in the field, then the current flows from high potential to low potential like this. So within the cell, current flows from low potential to negative high potential, just like if you see current electricity is a normal cell, the current flows from high potential to low potential outside the cell, but within the cell current flows from negative potential to high potential. So here you should not mistakenly write the current in this direction because the rod is behaving as a cell, so the current flows from negative potential to high potential. To find the direction of the polarity, we use right hand rule. One thumb keep the direction of motion of the rod, forefinger you keep in the direction of the field, then central finger gives the current direction. But the current direction within the rod is not from high potential to low potential because it is acting like a cell. Within the rod, current direction is from low potential to high potential. Like that we can find the polarity. Now, but when the rod is moving with the velocity V, from Lenz's law or conservation of energy, there will be opposite directions of magnetic field force will be created. So I is equal to BLV by R and magnetic force is equal to BAL, B square L square V by R. This also you can find out from the Fleming's left hand rule. Direction of the force will be left side direction, or according to law of conservation of energy or Lenz's law also you can guess that the whatever force that is created because of magnetic field will be left side. Suppose you want to maintain the constant velocity, you have to apply the same equivalent force of B square L square V by R right side. And the power to maintain this force, this velocity is given by power is equal to Fv, and Fv is B square L square V square by R is the power. So from current electricity, also we can prove that P is equal to I square R, I is equal to BLV by R, whole square R is equal to B square L square V square by R. Now let us find the EMF across the ends of a rotating rod. Let us consider a rod fixed at the end O on a smooth surface is rotating with a uniform magnetic field B existing perpendicular to its length. Here you cannot apply E is equal to BLV directly because length of each element is changing from point to point. Let us consider distance x, a small element dx, its velocity is x omega. Then the EMF induced in the small element d is equal to B dx into V. That is B dx into x omega. The total EMF is integration of from 0 to L. If we consider total length as L, B omega 0 to L x dx, that is equal to half B omega L square. Now, if the rod is fixed at the middle then in that case what happens, the EMF induced in this part and in this part will be opposite direction. Therefore total EMF induced will be equal to 0, and in this part that is equal to half b omega L by 2 whole square, and in this part also it is half b omega L by 2 whole square. Now if the rod or wire is in a different form, not a straight rod, then also you can apply this formula, provided you take the length from starting point ending point and you take the perpendicular component of velocity to the imaginary line we have drawn. So in this case EMF AB will be equal to BL V sin theta. Another famous problem is a semicircular ring is falling in a magnetic field vertically downwards. Magnetic field is perpendicular to the plane. Then what is the EMF induced across AB? EMF induced across AB is equal to B. L means effective length, like earlier told, 2R into V. Now we see the situation where a U-shaped smooth rod is there with the resistance R here. On that a resistance-less slider is falling down under the presence of gravitational field in a vertical plane and magnetic field in a horizontal direction B. Now in that case there is a mg force is acting. Let us suppose after a few seconds, a few milliseconds or few microseconds, velocity acquired by it is V. Then immediately there will be induced EMF in this rod because the flux is changed, because of motional EMF. Because of that you will get current, and that current is equal to BL V by R, and V is the velocity at any one instant. V keeps on changing. V is the velocity at an instant. So force will be equal to BIL PIL. So if you substitute I is equal to BL V by R, you will get acceleration is equal to mg minus BL by M, total force, g minus B. In the place of I, you substitute BL V by R, you will get g minus B square L square V by M R. And V is maximum when A is equal to 0. Therefore you can find V maximum is equal to mg R by B square L square. If you want to find the velocity at any instant, that also you can do it, provided you can write this A as V dV by dx, and you integrate this, then we will find the velocity at any position of the rod. From that you can find when the dx by dt you can find the position. So that depends on your ability of integration and knowledge of kinematics. And next, if you consider the rod, just earlier said example, instead of resistance, if you replace the resistance with the capacitor and connected to a rod and made it to fall down in a gravitational field, vertical plane, then at any instant of time, because of velocity of it, EMF will be induced at this end, because the capacitor is connected parallel, capacitor also having the same potential difference. So potential difference across the capacitor is Q by C is equal to potential difference is B L V. Therefore Q you can write as B L V C. Then differentiation is of this dq by dt, you will get as B L C dv by dt, but dv by dt is nothing but acceleration, so you will get B L A C. Similar to the earlier, A is equal to net force by mass, mg minus BAL by M. BAL in the place of I, if you substitute BLAC, you will get B square L square AC by M. If you simplify, you will get A into 1 plus B square L square C by M is equal to G, and A is equal to G by 1 plus B square L square C by M. And if you see another situation in which consider some rectangular wire with some part is removed, X part is removed in a perpendicular magnetic field B, it is moved with a uniform velocity V, then what is the EMF induced across A and B? See, if you consider this part also closed, according to Lenz law already we studied that EMF induced across them will be equal to 0. That means now whatever EMF you are getting, that is only because of this. Because even if this part will be cancelled out, even if this part will be cancelled out, because this part is anyhow parallel to the length, no EMF, this part is parallel to the length, no EMF. So the only EMF is equal to BXV. Also you should always remember, whenever you are applying E is equal to BLV, you should make sure that the magnetic field and length and velocity are perpendicular. If any rod is parallel to velocity or parallel to magnetic field, or then in that case the EMF across the ends of the rod will be equal to 0. If the rod is velocity is not perpendicular, then you should take one perpendicular component and then EMF will be equal to BLV sin theta. So EMF is equal to BLV you can apply provided magnetic field, length, velocity are mutually perpendicular. If any one of these two of these quantities are parallel to each other, the EMF across the ends of the rod will be equal to 0. Now we see finally, if you want to see this, consider infinitely long wire is current is I. Now at a distance A, we keep one square coil like this, one turn coil. Let us suppose at this instant of Newton's velocity is V. Then what is the EMF induced across this coil? If the magnetic field is uniform in the coil, then EMF induced will be equal to 0. But here, because of the current here, the field is less, more, and here field is less. So EMF and this part of the rod is parallel to velocity. So in this part EMF 0, in this part EMF 0, in this part EMF is equal to mu naught by 2 pi I by A into length B into V. And in this part EMF is equal to mu naught by 2 pi I by A plus B, because distance is A plus B. At that instant length B, velocity is V. So at this instant total EMF is mu naught by 2 pi BVI 1 by A minus 1 by A plus B. Why minus EMF is induced? Because induced direction will be same. So here in this case the EMF will be like this. Okay, when this is E1, this is E2, the net EMF from current electricity E1 minus E2, because when positive poles are facing each other, the net EMF is E1 minus E2. Only when minus plus is there, EMF is equal to E1 plus E2. Therefore, we have written net EMF is equal to this. Thank you. Bye.